Welcome to Industrial PLC Applications. And this video is a part of our Deeper Look series. Today we're going to be looking at understanding the contact states as displayed by Connected Components Workbench. PLC logic instructions have the familiar look of schematic symbols. The instructions are arranged in a schematic ladder diagram format and are arranged in a language, if you will, that electricians are familiar with and can understand. Once programmed and downloaded to the PLC, however, they're converted to machine language when transferred to the processor. The coils and contacts displayed, however, are not real-world physical devices. They are actually instructions for the PLC to follow and the order in which they are to be followed. These instructions can be a read type, where the CPU will evaluate the value or state of a variable, or a write type instruction where the CPU will write a new value to a variable or change its state. In logic and digital electronics, there are only two states: the absence of voltage or the presence of voltage. All digital electronics and PLCs and CPUs work in binary. Even non-binary values are simply converted into decimal through software for human understanding. The problem is, there are a lot of different ways to express these two states. Let's take a look at some of the synonyms used to evaluate and express the voltage presence or the voltage absence. So looking at voltage absent, the following terms are used to describe it: zero, off, false, low, unset, no logical path, or de-energize the variable or write a zero. Voltage present has the following: 1, on, true, high, set, a logical path, energize the variable, or write a 1. Logical continuity dictates or determines whether an output will be energized or de-energized. It is a logical path of true or false instructions will determine the value written to an output: a 1 if there's logical continuity, or 0 when continuity does not exist. Logical continuity will occur if all instructions in a series arrangements are true, or if any parallel connected branches become true, or if any combination of series and parallel connections provides a logical path to a device, will be considered logical continuity and the output will be energized. Any other combination will be considered logical incontinuity and the output will be de-energized. In Connected Components Workbench, instructions or variables that are false are not highlighted and will appear in blue or the default off color. When a rung is read from left to right and does not complete a path of logical continuity, the output will be logically false and a value of 0 will be written to the output variable's memory location. In Connected Components Workbench, instructions or variables that are true are highlighted and will appear in green in version 22 or red in version 21. When a rung, read from left to right, completes a logical path of continuity and all instructions as shown are highlighted, the result or output will be written as true and a value of 1 will be written to the final output. This rung appears to break the rules. The second instruction seems to contradict what we have learned. The text above the instruction is red, indicating the PLC has detected a voltage, but the instruction is shown as de-energized. Although it looks confusing, it's actually a common occurrence. It can indicate one of two possible conditions. The second instruction is identified as a real-world input, IOEMDI01. If you examined the PLC's input LEDs, you would see that DI01 is active. Therefore, the red text is correct. But here, the instruction does not provide logical continuity. The reverse contact instruction tells the PLC to look for the absence of a signal. Since the signal is present, the PLC resolves that the condition requested is false, and the logical continuity is not satisfied for this instruction, so it is shown as being false. This is an important concept you must keep in mind. It's not the signal state that matters. It's what do you want the PLC to do with each possible state. Another way to think of this is you can use both the on state and the off state of any variable. With an electrical circuit using a single pole, single throw switch, the state of the switch is physically limited to report its on state. That is, it demonstrates the light is on by passing a current to the lamp. But the light switch being in the off position cannot be properly determined, since a burnt out bulb shows the same condition. Earlier, we mentioned there were two possible causes for the true, not true situation. Here is the other. The rung above clearly has logical continuity, but one of the outputs is off. This is normally the result of a duplicated output instruction in how the PLC solves the logic during a logic scan. This is covered in detail in another video. The PLC, however, acts like a large variable junction box. We can apply both states by making logical connections. Here, by using branching, we make use of both the on and the off states of the same variable to control two different outputs. In Connected Components Workbench, active true instructions are displayed in the active color, while inactive or false instructions are shown in the inactive or false color. The true value of the variable is shown by the color of the text. The color of the instruction indicates the final value resolved by the logic itself. In other words, what the PLC is interpreting or doing about the value of the variable. Thanks for watching. Other videos you may be interested in watching are the PLC scan, the cross-reference browser utility, and the variable monitor utility.